We've made extended use of the metaphor of a vending machine as a function in this, and for good reason. It's a great way to understand what's going on with a function. We're going to use it again today, but I want to start it off from this perspective. Take a typical vending machine, and we're looking at this as people who use them, not necessarily as people who build them or repair them or anything like that. But as a person who uses a vending machine, what are the important parts? In this video, we're going to be identifying the parts of a function as represented by what's called function notation, and we're going to evaluate functions from whatever representation we'd like using function notation. So if we look at a vending machine and we talk about the parts that are really important to us, the parts that really stand out are the part where you put in money, the part where you push a button, and the part where whatever food or drink you want comes out. All of that stuff, or all the other stuff, really is kind of inconsequential. We don't care as much what's going on behind the scenes, so long as we push the button and whatever we want comes out. Well, in terms of a function, we can actually describe what's going on there using terminology from functions. We have the domain is the input or the starting value. So we put our money in and we press a button, and that's where we start out with this thing. So our input, our domain, is a button that we press on there. The function is the stuff that happens to the input. So that's the vending machine itself. And again, we may or may not care what goes on behind the scenes, but there's some input, a button that I press, and that goes into the vending machine, and some magic happens, whatever that magic may be, and then something comes out. We call this the range, the output. So in this case, the output would be food or drink or whatever we're getting out of the machine. And so here you can see those important parts, the button and the part where things come out, are important as well when describing functions. Now I'm going to rewrite this over here, and then we're going to look at a specialized way of writing this. So we've got the button, which leads to the machine, which leads to our output, our food or drink. And what I want you to do, and this is a part where I want you to actually do this in your notes, is we're going to describe these with different symbols so that we end up with a way of describing all of this in a very compact and easy to understand way. So for our domain, the button, we're going to call that X. So our domain is X. Whatever we want that to be, doesn't matter. Could be a button, could be a number, whatever. That's the input to our function. And then we have the machine itself, the function, and we're going to give that a name. And what we call it is pretty inconsequential, but there's a general name that we use. We call functions F because we're really not all that creative, and more because we want it to make sense. So F makes sense as a function. So X is my input, and I put that into F, and I get my output, which I call F of X. And so what I see here is my input, my domain, which function is happening, and then collectively this whole thing right here together is my output, my range. And so when it's all put together, it might end up looking something like this. F of X equals, and then whatever, let's say I got a Dr. Pepper out of the machine. My output is Dr. Pepper, but in calling this the output or the range, I can still see the name of the function and what the domain was inside my representation of the range. So it's a very nice, quick way of seeing everything that's involved. And so what we're going to do now is we're going to look at how to use this to do what's called evaluating different scenarios. So let's look at example 1 here. A function named f contains the ordered pair 5, 9. We want to write this in function notation. So my function is named f, so there I have my name, that's important. And I have this ordered pair. And an ordered pair always has an x and a y. My x is always my input, which we also call domain. My y is my output, which we also call range. And so what I do is I'm going to use 5 for x, 9 for my output. So I would say f, because that's the name of my function, f of 5, and remember that's read f of 5, so function with an input of 5 is equal to 9. And this is that same thing that I just wrote up there, written in function notation. So I can see my domain, my input, is the part inside the parentheses. The name of my function is the part on the outside of the parentheses. And when I take that all together, that's my range, that's my output, which is 9. You can also kind of see our ordered pair hiding in this. 5's right there, 9's right there. So again, this is just another way of writing what's going on in the function, only this time it allows us to give the function a name. So let's look at example 2. Now this one is strictly speaking evaluating. I've got this function g, which is given by a set of ordered pairs, and I want to find g of -3. So g of -3, the g tells me I'm dealing with this function. That would be important if I had multiple functions there. And the -3, remember, is an input. This is an x value. So what I want to do is I want to find -3 as an x value. And I have to be careful because there it is as a y, there it is as an x. So here it is as an x value. And my question is, what is g of -3? Well, taken all together, that's asking for a range value. So the range value that goes with -3 is 2. So I would say that g of -3 is equal to 2. This is just a fancy way of saying, hey, when my x value is -3, what's my y value? Well, it's +2. And again, you can see the ordered pair hiding in there. So my final answer to this, if I'm wanting to find g of -3, g of -3 is equal to 2. We can do the same way going the opposite way. Now I'm given that g of x equals -3. So in this case, I know my y value, because remember, g of x taken all together is my y value. So I know my y value is -3. So I look through here for -3. There it is. And I'm wanting to know what x is. What is the domain that gets paired with -3? And there it is right there. X is equal to 5. So finding x when g of x is equal to -3, x is equal to 5. Now it's not just ordered pairs we can do this with. We can do it with a table. And since we now have names, I can talk about multiple functions going at once and work from there. So for example 4, I'm supposed to find h of 1. So I'm given a domain value of 1, but look, I have two functions. I have g and I have h. G is the ordered pairs, h is the table. I know the x value is 1 in h, and I'm wanting to know what the y value is. So look over here in h and look for 1 in the domain. There it is, and that's paired with a -3. So we would say that h of 1 is -3. It's as easy as that. Now I'm asked to find x if g of x is equal to -4. So this is saying that the range value, all of this taken together, is -4. And I want to know what the domain value that goes with that in function g. So now I'm just looking at function g, and I want to find a y value of -4. Well, there we go. My x value then would be -2. So g of -2 is equal to negative 4. So that's why we have the names. That way if I have multiple functions, I can tell the difference between them. And we can do it for graphs. There's nothing that says we can't. We're supposed to, in part A, find f of 5. And so we say f of 5. That means I want a domain value of 5. So I look over here. There's my domain value of 5. There's the only point involved with that. And so I can see, if I write out the point, this is 5, 0. So when the x value is 5, the y value, the range, is 0. So f of 5 is equal to 0. And for part B, find x if f of x equals 2. So that means when my range, when my y value is equal to 2, well, there's only one point with a y value equal to 2, and that's the point negative 3, 2. So I would say that x is negative 3. So when the range is 2, the domain has to be negative 3. All of this is called evaluating a function. So that is finding the range value when the domain is this, or finding the domain value when the range is that. All of that is evaluating a function. You're finding a specific value at a specific point. But it turns out we can do this with equations too. And this is unbelievably powerful. So let's take a look at this right here, because a lot of people get messed up with the notation right here. F of x equals x plus 2. This, the x plus 2 part, is what's called a function rule. So if we go back to our vending machine, x is still the button that we push, and f of x taken together is still the thing that we get out of the vending machine. The difference is this time we're shown how the machine works. We're shown that we take whatever our input is, whatever our domain is, and that we add 2, and that gives us the range. So this is almost like if the front of our vending machine was open and we could see how the machinery inside was working, so that we could understand a little bit better where our stuff is coming from. So I'm wanting to find f of 5 for this. So the way I do this is now I want to find f of 5. That is, I've replaced this unknown x value with a known x value. And so over here, I'm just going to replace that x with a 5 as well. Now this is where you have to be careful. Over here, the f of 5. This is just a name. This is not anything that's requiring multiplying f times 5. We've used this in the past to just say this is our range value. That is all this is. This is just saying that the range value is equal to 5 plus 2. No math gets done with this. It's a name, it's a label. So knowing that, I just leave that the heck alone. It is f of 5 equals, well, 5 plus 2 is 7. And now I've answered the question. I've found f of 5. F of 5 is equal to 7. All I did was substitute in my domain value for x. Now, of course, this can get very complicated. We can have a big, nasty expression like this, but it turns out that it changes nothing. It's still the same stuff that we've already done. I want to find f of negative 5. You know what, let me write the problem here first. F of x is 2x squared minus 3x plus 2. Now you might see this and be tempted to distribute. You can do that first if you want to, but hang on with me. There's an easier way to do this. I'm trying to find f of negative 5. So I replace all my x's with negative 5. Notice that I'm putting it in parentheses. That'll be important when we square it. Minus 3 times negative 5 plus 2. And so now all it is the order of operations. Do parentheses first, then exponents, then multiplication and division from left to right, then addition and subtraction from left to right. So when we do this, I'm going to do my parentheses first, and so I do everything inside the parentheses. 3 times negative 5 would be negative 15, And then negative 15 plus 2 would be negative 13 inside the parentheses. Next up, I need to do any exponents. And so here I have an exponent of 2. So that would leave me with 2 times negative 5 squared, means negative 5 times negative 5. So that would be 25 minus negative 13. Notice that it's minus and then inside here is a negative, so that is in fact minus a negative. Now I do any multiplication from left to right. 2 times 25 is 50. And then when I do 50 minus negative 13, well, that's the same thing as 15 plus 13. And so f of negative 5 is equal to 63. So again, the big idea there, follow the order of operations. So to recap, function notation's just a shorthand way of describing the relationship between the domain and range. Functions have names. We can use these names to identify them. So if we've got a bunch of functions, we name them so that we know what to call them. Sort of the same reason we have names. The parentheses in the f of x part, not multiplication. It's just a label, just a name. And function rules are just lists of instructions. Substitute in your domain value, follow the order of operations. If you don't know the order of operations, go back and learn it. If we don't all use the same order of operations, we end up with different answers, which is less than ideal.